In part 2 of this lesson, we'll continue answering where we left off. And in question 2, they ask, link L is pivoted at B, but slides along the fixed point P. As slider C moves in the slot at a constant rate of 4.26 centimeters per second, the angle theta changes. Find the rate at which theta is changing when S is equal to 6 centimeters and theta is equal to 55 degrees. They've given us very little to work with here. The only thing that they tell us is 4.26, which is the rate of change of C, and they want us to find out the rate at which theta is changing when S is equal to 6, so when this has moved 6 centimeters, and that occurs at an angle of 55 degrees. What we can do to start is see how side S, the opposite side, and the angle relate to one another. So let's pretend we had a right triangle here, and this was our angle, this is our opposite, and this is our adjacent. What we are using here is tangent. Tangent theta is equal to our opposite, which in our case is 8.63, over our S value, which varies, of course, depending on the time. Therefore, we can say S and theta are related by tangent. What we can do from here is solve for S and then take the derivative with respect to time. Because if we do that, then we can substitute 4.26 with ds over dt. Let me show you what I mean. So let's solve for S. We end up with S is equal to 8.63 over tangent theta. Like I said earlier, if we take the derivative now with respect to time, then we can start substituting many important pieces of information here. So let's take the derivative of the left side. We have to do this implicitly. Taking the derivative of S gives us ds over dt. And later we'll substitute 4.26 into this expression. And over here we have 8.63 over tangent theta. Remember that we can split this into 8.63 times 1 over tangent theta. The reason why I'm mentioning this is because 1 over tangent theta is equal to cotangent. And we can use this relationship to find the derivative of cotangent quite easily. So let's go ahead and do that. Let's switch this to 8.63 times 1 over tangent theta, which is similar to 8.63 tangent theta. And the derivative of cotangent is negative cosecant squared theta. So let's write down 8.63 times negative cosecant squared theta. And now we have to take the derivative of this with respect to time. And that is equal to d theta over dt. Next, we will substitute what we know, 4.26, into here. And remember what they're asking. They're asking for the rate of change at which theta is changing when S is equal to 6.00 and theta is equal to 55 degrees. So what we have to do is solve for d theta. We'll start by replacing this with 4.26 is equal to, and dividing both sides by this part. This will isolate for d theta over dt. So divide both sides now by negative 8.63 cosecant squared theta is equal to d theta over dt. Now the reason why this is a good thing is because now we can split this up where we have 4.26 divided by negative 8.63, and at the same time we have 1 over cosecant squared theta. Remember that cosecant theta is equal to 1 over sine theta. So if I squared this and I squared the right side, I would end up with this part changing to 1 over sine squared theta is equal to d theta over dt. Cleaning this up a little bit, I get 4.26 and 8.63 at the bottom, and at the top I end up with sine squared theta is equal to d theta dt. Now all I have to do is substitute 55 degrees into here. Now using our calculator we end up with negative 4.26 times sine of 55 to the power of 2 divided by 8.63 gives us negative 0.3312. Negative 0.3312 units per second is equal to d theta over dt. This tells us that per every second, the ratio in which the angle makes decreases by 0.33. That's the answer to question 2. Make sure that you watch question 1 if you still don't understand how to find the derivative of secant and cotangent functions.